Okay. So with the solutions unit, it butts up against intermolecular forces unit because the solutions really have a lot to do with how intermolecular forces are utilized, and then those forces are overcome. But we're going to talk about how to identify a solute and a solvent and explain and be able to determine whether or not something will dissolve, and then identify what happens with an ionic or covalent compound and draw a diagram of it when it's dissolved in water. But we should recall a couple of things. So when we talk about whether or not something is ionic, we're talking about whether or not there is a metal and a nonmetal present. We're talking about electrons are transferred. Uh, from to the nonmetal. And the as a result of the electron being transferred, ions are formed. So positive and negative. Ooh. Things that what makes something covalent? Well, that would be when you have a nonmetal and a nonmetal. Electrons are shared in covalent bonds. And molecules are formed that are polar or nonpolar. And then what does it mean to dissolve? Well, there's some definitions that we're going to talk about in terms of what it means to dissolve, but I think that the easiest way to, just define dissolving is when one substance gets surrounded and engulfed by another substance and broken into its pieces. So, yeah. So one substance uh, is broken into its pieces or parts. Oh, I think I spelled that wrong still. Jeez. Parts it is. Into its parts and surrounded by another substance. And the issue with that, I guess that's what it means when something dissolves. But there's two definitions that are really kind of important in terms of understanding that. And I get that that's a little wordy and a little vague. But the reason why is because we hadn't talked about the definitions yet, and those definitions are coming up now. And so the new definitions that we're going to be talking about are solute and solvent, and you may have heard of these before, but I want to define them now. So the solute is the substance that gets dissolved. We, in our personal experience with things that are dissolving or being dissolved, a lot of times will think or feel like a solid thing will dissolve. So examples of solutes would be things like sugar or table salt or Kool-Aid or I don't know, other stuff that dissolves. But solutes can be solid, and in this class, they're mostly going to be solid, but they can also be liquid, and they can also be gases. So we're going to really focus on the solid parts of solute. Solutes are usually found in smaller amounts. And then the solvent, the solvent is the substance that does the dissolving. And in our personal experience, more often than not, we usually think of that as a liquid, like water, but it can be a gas and it can be a solid as well. And the solvents are usually found in larger amounts. So we have the solute, which is the thing that gets dissolved. We have the solvent, which is the thing that does the dissolving. And a lot of the reason why solutions occur, why solutes get dissolved by solvents, has to do with intermolecular forces of attraction. So I'm going to roll through here and do a couple of examples. So we have a gentleman named James who decides to make the Kool-Aid and stirs 15 grams of Kool-Aid powder into 1 liter of water. And our task at this point is to identify which is the solute and which is the solvent. So, what color is it? Okay, so in this case, the solute would be Kool-Aid. And the solvent would be water. How do we know that? Well, there is a solid and it's being dissolved in water. There's a solid being placed into water. So there's solid is in smaller amount than the water. So you might say solid is in a smaller amount. So that's one example. Another example would be this picture, which might be easier to see solute versus solvent. So here we have CO, which is carbon monoxide, and then H2O, which is X, which is your water. It looks like in this case, the CO, the carbon monoxide, is surrounded by water particles. So that and the CO is not touching another CO molecule. So it looks to me like the CO has been dissolved, so that would make it the solute. So the CO is the solute, and the water is the solvent. And in this picture, we can probably be able to reason or explain that because the water is completely surrounding the solute molecules. And then we have yet one more example here where we have brass, which is made up of 34% zinc being dissolved in 66% copper. So in this case, I would guess or reason that my zinc is my solute, and my copper is my solvent. And in this case, it might be really easy to say, well, because the problem says it's being dissolved in. But another way to look at it would be the zinc is the smaller amount. So that's the solute. Now, when we have a metal being dissolved in a metal, that's a very, very special type of solution, and we call that an alloy. So it's a metal dissolved in another metal. And a lot of times the reason why we would make things that are alloys in the first place is simply because the two metals by themselves are not as strong as the metals combined. So that's kind of why you'd want to do that. So iron is really, really pretty strong, but then steel is even sort of stronger because it's a combination of a bunch of different metals. So questions about this so far? So, what determines if a solute will dissolve in a solvent? Okay, so this is our next thing that we're going to talk about. And we know that covalent compounds, like if I take a covalent compound, like in this case, sugar, which happens to be sucrose, and I have a pile of sucrose crystals laying around, that sugar is being held together. The individual molecules of that sugar is being held together by intermolecular forces of attraction. So that's really what's holding them together. Specifically speaking, in this instance, the sugar molecule itself, because I see a lot of different things going on here. Hopefully we know that because it's a molecule, it's going to have London dispersion forces, or LDF. I also see a lot of OHs here, which would tell me that there are probably, that means that there's going to be hydrogen bonding. And at each of these points, like on this diagram here, each of those points is a carbon, right? And you may recall from last unit that carbon usually, when bonded with oxygen, created a dipole. So this is going to be dipole-dipole as well, which means this molecule is going to probably most likely be a polar molecule. So if I was going to draw a sugar diagram for MOM diagram for sugar, I'm not going to draw all that business because that seems like a lot of shapes. So I'm just going to do three separate shapes. So I'm going to do something like carbon will be, let's say, a square, and then hydrogen will be a triangle, and then we'll say oxygen is a circle. So if I was going to draw this as a shape, I'm just going to really simplify this structure. I'm just going to have them kind of all bonded together, and I'm going to do a few of them. So it will look something like this. And so they would be bonded together. So they're actually held together by bonds, right? Because they're sharing electrons. And then the other thing, too, that we're going to kind of think about here is that there's going to be some intermolecular forces of attraction holding them together. And so I would probably represent that by like this. Okay, so they're being, the intermolecular forces of attraction are holding that particular crystalline structure together. Questions about that so far? All right. Water has been referred to as the universal solvent. What that means is that it tends to dissolve a lot of things. Water is a really, really, really special compound in the grand scheme of compounds. So I'm going to try to talk about that briefly now. So we know that water has, because it's a molecule, right? Because there's covalent bonding, it's going to have LDF, but it also has a special type of dipole-dipole, which is just hydrogen bonding. And since there are dipoles on this particular molecule, delta negative, delta positive, this is a very polar molecule. And in an effort to sort of draw that, purple and green, I'm just going to continue the same format here. So oxygen is purple and a circle, and hydrogen is triangle, hydrogen. So if I draw a bunch of those, they would look something like this. And I'm going to show my bonds. And then I'm going to show my intermolecular forces of attraction between the positive thing and the negative thing, something like that. Okay. Now, technically speaking, going forward, we're going to go back to drawing water like this. We just don't have time, space, effort to draw all of the individual waters, but I am going to do it a couple of more times drawing the waters as we go forward so you can see some things, hopefully. So in order for sugar to dissolve in water, and we know sugar dissolves in water because of our experience of sugar in water, we would have to think about the fact that sugar is polar. Water is polar. And that's really pretty important. So what I'm going to do is I got to go back up and look at my colors because I forgot. Red, triangle, red, green, or purple. So we're going to say that sugar, so carbon was square, hydrogen was a triangle, and oxygen was a circle. But for water, I'm going to do it all in one color, sort of to illustrate the fact that oxygen and hydrogen are like that. Okay, so I'm going to draw this. I'm going to draw a few of these molecules here in an effort to kind of illustrate that whole situation. So here I have carbon, and maybe another carbon, and maybe, I don't know, another carbon, and hydrogen. Oops, that's an A. Say a hydrogen, and say a hydrogen, and then an oxygen, oxygen, and oxygen. And I'm going to probably try to get those a little closer together. And then I'm going to draw something that looks like that. Now, what I'm going to attempt to show here is that the water molecules are surrounding each of the individual sugar molecules. So that would look something like this. And this will probably, wow. Jeez. I am taking the time to sort of illustrate the point that when something dissolves, it gets entirely surrounded by water particles. So going forward, you're going to be allowed to draw X's, but I really do want to take time to show that these particles, these molecules, are being completely surrounded by water. Okay. Now, so in order for sugar to dissolve in water, the intermolecular forces have to be the same. So this only works because sugar is polar and because water is polar. Okay. If that was not the case, then this would not work. So we should probably talk about an example where that might not be the case. You ready, or are you still drawing? All right. The next molecule that we're going to discuss is hexane. Okay. And I see that these are all covalent bonds. So it's all nonmetals. So this is going to have London dispersion forces for sure. I don't see any evidence of dipole-dipole. I don't see any evidence of hydrogen bonding. So, and I also see that this structure is pretty balanced. So this is going to be a nonpolar molecule. Now, if we know that water is polar and hexane is nonpolar, I mean, technically speaking, nothing will happen. But if I want to draw a picture of what that would look like, so I will. Here I'm going to have my water. And on top of it, I'm going to have hexane, which I'm going to say C is a square, H is a triangle, and they're just kind of sitting on top of the water. Like, that's kind of it. So they're not, I mean, they can touch, so maybe I should make my water a little bit better. So it looks like they're sitting. But the water is not going to dissolve the hexane because the hexane has not, the forces of attraction with hexane are so slight that water won't do much to it. But does that mean that hexane can't dissolve or get dissolved in something? No, it just means that hexane has to be dissolved in something that's non-polar as well. So thinking about like that, Sharpies work great because if you draw like on a table or the floor or the wall and you just take good old-fashioned water and you try to get the Sharpie to go away, the Sharpie, the molecules inside the Sharpie are nonpolar and they don't dissolve in the water, so they stay, right? But if you take something like rubbing alcohol, which happens to be nonpolar, and you take the rubbing alcohol and you put it on top of the Sharpie ink, you can get the Sharpie ink to disappear in large part because the Sharpie is nonpolar, rubbing alcohol is nonpolar, and you are essentially dissolving it when you do that. So, science. Now, the last couple examples here that we need to talk about are ionic compounds. So, ionic compounds are held together. They're held together by transfer of electrons or ionic bonds. Specifically speaking, we're talking about the ion-ion interaction. So if I was to draw FeCl3, I would start with maybe, I don't know, Fe will be my square, chlorine will be a triangle, and I'm going to draw this structure, and I'm going to kind of get ahead of it. So I'm going to have Fe, and okay, and then chlorine, and I'm kind of getting ahead of the game here, showing it's already bonded together. And I'm purposefully choosing a different color here for the last electron around chlorine because I want to indicate that that electron has been transferred. So now fluorine has a +3 charge, and chlorine, each of those individual ones have a -1. And so that's a charge right there. So that's ionic charge. Which is like the super strongest dipole you can have, right? And we know that water is superpolar. So because water is as polar as it is, it can attract the charged ions and separate them out from the solid iron chloride. And so what ends up happening is when you take an ionic compound and you dump it into water, that ionic compound will separate into its individual ions, and those ions will be surrounded by water, which would look something like this. And then we're going to show that the water, and I'm not going to draw all the individual waters, but would do this. So in the past, when we drew MOM diagrams, we just kind of drew like a big structure and then like put X's around it. But now we're going to add a layer to that that says that if you have an ionic compound, it gets separated into its pieces, and water surrounds that. So I'm going to kind of draw a couple of instances down off to the side so you can see it. So if iron is a +3, water would orientate itself like this. Where the negative oxygen would be attracted to the positive iron, right? Negative, 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 negative. And then chlorine, similarly, would look something like this. So I guess I'll do chlorine over here. The positive part of water would orientate itself around the chlorine. And I'm just going to do that. So that's what happens when you dissolve an ionic compound into water. Ions are charged. Water is superpolar, so it's basically charged. And you end up with that situation there. 59. We're doing fantastic. All right. Last thing we got to do here before we move on is we're going to go through a couple of examples to determine whether or not a compound is ionic or covalent, then draw the MOM diagram of the substance that would be dissolved in water specifically. So CaCl2, I see that we have a metal And chlorine is a nonmetal. So that means that this is ionic. So that means it's going to separate into its parts. So I see that chlorine, or calcium rather, will be a +2 because I'm on crisscrossing, and chlorine will be a -1. Okay. So what that would look like would be something like this. And it would absolutely be dissolved, separated, surrounded by the water. CO2 is a nonmetal and another nonmetal. So that means it's covalent. And as a result of it being covalent, we have to decide whether or not it's polar or nonpolar, really, in reality. And I'm going to tell you, because I'm going to draw it down here for you. That this is going to be what type of molecule, polar or nonpolar. There's dipole charges that are in opposite, but they're equally pulling in opposite directions, so they cancel each other out. So this is going to be nonpolar. So what that would look like would be this. Oops. Where they are not dissolved. And then lastly, I see that I have a metal, which is sodium, and a polyatomic ion, which is phosphate. So that makes this ionic. So if I see that sodium is a +1 charge, and if I look at the back of my handy dandy periodic table, I'm going to see that phosphate is a -3 charge. So if I drew and something like this, well, at that point, oops, we don't want red water. That's terrible. So then we're just going to surround each of the individual ions with water. So in this instance, ionic compounds dissolve in water. Covalent nonpolar compounds do not dissolve in water. Polar covalent compounds do dissolve in water. And that's the big takeaway from today. Questions? Excellent.